Theorem 9.11, Convergence of P Series. The P Series equals or converges if, there we go, if P is greater than 1, and it diverges if the power P is greater than 0, okay, but less than or equal to 1. All right, so let's look at a couple of examples. Okay, if you're given this set of series and you're asked to determine if it converges or diverges, again, you might want to first check to see if the series are geometric. None of these are. So the next thing is you might want to look at the nth term test for divergence. And if you find the limit as n approaches infinity of any one of these terms, you're going to see that it goes to 0, so that produces no results. Okay, so but all of these you just need to be able to identify our P series. So the power here is 1, the power here is 2, and if you rewrite this denominator as n to the 1/3, the power is 1/3. So you can just easily identify that. There's not any work to be shown. You would just say this is divergent harmonic series with P equals 1. It would be just fine to say divergent P series. Harmonic is just the special case where the power of the P is 1. Okay, looking at this right here, this is a convergent P series with P equals 2. So when the power is greater than 1, it converges. So convergent P series with P equals 2. So if you're asked to, state whether the series converges or diverges and it's a P series, this is all you have to say. Okay, and for this third example right here, because P, the power is between 0 and 1, or equal to it, you would say this is a divergent P series with P equals 1/3. Okay, and as a final example, we're asked, does this series converge or diverge? Again, just trying to remind you about the checklist. This is not geometric, so we don't have any information from that. The nth term test for divergence says look at the limit as n goes to infinity. Well, your denominator is going to get super large, so that limit would be 0, so there's no results there. Can we use the integral test? Well, the conditions that have to be met is, okay, if we were to model this with the function 1 over x ln x, is it positive, decreasing, and continuous? And yes, it would be. Okay, so that's what we're going to do, use the integral test. Notice that we begin with n equals 2, and if you think about why that is, if we began with n equals 1, okay, that's not a problem here when n is 1, but right here there's a problem. Natural log of 1 is 0, and we don't want to divide by 0, so we just consider this series starting with 2. Okay. Okay, let's model this with an improper integral. Let's rewrite it as a proper integral. Okay, we need to begin to think about how to integrate this. Well, we're going to use u substitution. U is going to be the natural log of x. So the derivative would be 1 over x dx. So we don't need to bring in anything. 1 over x dx will be replaced with du, and then we have natural log in the denominator. So that'll be our u in the denominator. Okay, switching over to a u integral, again, we're going to have 1 over u, this is u, and everything else gets replaced with du. So we end up with the integral du over u. The antiderivative is the natural log of the absolute value of u, which happens to be natural log of x. It's kind of odd. from 2 to B. Okay, let's do the evaluation part. So natural log, absolute value, natural log of B minus natural log, absolute value, natural log of 2. 2. Okay, now we can insert infinity for B and drop the limit. Okay, and then just kind of doing the evaluations here. I don't think I need an absolute value here. Okay, so natural log of infinity, again, think of the natural log graph. Natural log of infinity is infinity. That's infinity. And then again, on the outside here would have the natural log of infinity again. So that would be infinity minus natural log, absolute value, natural log of 2. Okay, well, infinity minus this small value is still going to be infinity. So what does that tell us? It tells us that the integral diverges. So if the integral diverges, then the series that I'm modeling with that integral is actually going to converge. So therefore, by the integral test, the series diverges. So there's the integral test, and part of that, a subset, is the P series and the harmonic series, because we can model those P series and harmonic series with an integral. So it fits nicely in this section.